All right, welcome, ladies and gentlemen. The lecture you're about to listen to here is a lecture which contains information that will be extra credit on your nomenclature and bonding test regarding the naming process for ternary acid ions and compounds containing ternary acid ions. So, without any further ado, let's go ahead and get started here. A ternary acid ion is the species which we form when we disassociate a ternary acid as it dissolves into aqueous solution. For example, you might look at an acid like, let's say, HClO3. HClO3, you notice here, is a ternary acid according to the naming conventions we've dealt with so far, in that it has hydrogen, a nonmetal, and oxygen bonded together. And the key idea here is that when you put a species like HClO3 into an aqueous solution, that species disassociates into its component ions. To disassociate, again, means to split apart. So as this species disassociates, it separates into a hydrogen cation, and then the anion is ClO3, 1 negative. And the idea we want to look at here is we want to be able to name this ion formed from that disassociation, the ClO3, 1 negative ion. And the names of these ternary acid ions are derived from the names of the acids from which the ion itself is derived. So what we're going to do is start by looking on your common ion sheet and identifying the parent acid. So if you have a look at your common ion sheet here, you'll notice here that the species HClO3, listed in the bottom left-hand corner there, is given the name chloric acid. And we're going to check to make sure that the number of oxygens in our parent acid is the same as the acid we're looking at right here. So you'll notice that HCl3 is in fact the parent acid, so we don't need to change the name any further. At that point, what we're going to do is we're going to have a look at the ion formed from the ternary acid ion as it disassociates, following the conventions where we're going to change the name of ic acids to ate ion and us acids to ite ion. So recognizing that chloric acid is an ic acid, the name of the ion formed from the dissociation of chloric acid would therefore be the chlorate ion. Again, recognizing the ic acid generates an ate ion. So far, so good. We could look at another example. Let's take a look at, let's say, the species HClO2. For having looked at HClO2, again, upon dissociation, this would form a hydrogen ion and a ClO2, 1 negative anion. And now to name that ion now, the ClO2, 1 negative ion, we have to look at the name of the acid from which it was derived. So HClO2 is a ternary acid ion in the chloric acid family. However, that acid has one fewer oxygen than the parent acid, chloric acid. So according to our naming conventions for ternary acids, the species HClO2 would be, therefore, chlorus acid, as we change the suffix from ic to us if there's fewer oxygens than in the parent. At this point, we can now name the anion formed from the dissociation of chlorus acid. According to the conventions that us acids make ite ions, that would make the ClO2 negative 1 ion into the chlorite ion. So again, ic acids make ate ions, and us acids make ite ions. One other thing to watch out for is the possibility of dealing with a species which is a ternary acid that disassociates to make multiple ions through the dissociation sequence. This is what we call a polyprotic acid. So let's have a look at the species here before we move into the other examples listed on here. Something like, say, H2SO4, a familiar acid, which is sulfuric acid. If we look at the species H2SO4, upon dissociation into its ions, this separates into an H-positive cation and the HSO4, 1 negative anion, which can then further dissociate into a second H-positive ion and the SO4, 2 negative ion. And at this point, we recognize now that the dissociation of the acid H2SO4 forms two different ternary acid ions as a result. And we need to be able to name both of those according to our conventions. So again, following the process, we're going to identify first the parent acid here. The parent acid off of your sheet, H2SO4, is named sulfuric acid. And that is, in fact, the parent acid, so we don't need to modify the name any from there. So sulfuric acid is what we're starting with. We now recognize that ic acids yield 8 ions, which implies the ion SO4 negative formed from the dissociation of sulfuric acid will therefore be the sulfate ion, again, ic to 8. And then that intermediate ternary acid ion, the species HSO4 negative, is simply modified by adding the prefix hydrogen. So therefore, that species HSO4 1 negative is the hydrogen sulfate ion. All right, so that's pretty much the process. Let's go ahead and look at a couple more examples here, see if we can kind of come up with a couple of names for these two species here that we've got listed on our examples. I'll move this off down to the bottom here so we can keep it out of the way for a moment. And let's take a look at the name of the species HSiO2 1 negative. That species HSiO2 1 negative is a ternary acid ion derived from the dissociation of an acid in the silicic acid family. Silicic acid has a formula listed on your common ion sheet of H2SiO3. So that's the parent acid. Our ion has fewer oxygens than the parent acid, which means we first need to modify the name of our acid. So this ion, HSiO2 1 negative, would have been derived from the species H2SiO2. So if H2SiO3 was silicic acid, and the species H2SiO2 would be, according to our naming conventions for ternary acids, one fewer oxygen, which would make this silicous acid, as we change the ic to us when we subtract one oxygen. So that acid, H2SiO2, upon dissociation, would split apart into the following ions, H positive and HSiO2 1 negative, which is going to further split apart to another H positive and SiO2 2 negative. And again, we're going to follow our conventions now. Since the acid H2SiO2 is an us acid, that is silicous acid, us acids make ite ions, and as such, the ion derived from silicous acid is the silicite ion. And then the one that we're looking for, that species HSiO2 1 negative, gets modified with the prefix hydrogen, meaning this species is therefore the hydrogen silicite ion. So there we go, we've got hydrogen silicite ion. Let's do one more example right here. The species listed now is SeO3 2 negative. Having a look at the species SeO3 2 negative, again, we need to start by identifying the parent acid off of your sheet. The parent acid here is H2SeO4, and that acid is selenic acid. Recognize that, again, our species has fewer oxygens than the parent, which means this must have been an ion derived from the dissociation of H2SeO3. To name that, we would change the ic suffix to us, again, with one fewer oxygen. So this would be selenous acid. And then we can look at the dissociation that would produce the ion we're looking for. The dissociation of selenous acid, H2SeO3, would follow the sequence in which it separates to H positive and HSeO3 1 negative, which would then further dissociate to another H positive and SeO3 2 negative, the ion which we are looking for. So now last, according to our conventions here, we can go ahead and start our naming. This species right here, H2SeO3, was selenous acid. Us acids make ite ions. Therefore, selenous acid makes the selenite ion. And if we wanted to, we can name the species HSeO3 1 - 2. This again will be the hydrogen selenite ion. All right, so at this point we essentially have naming conventions now for deriving the name of ions from the dissociation of ternary acids. Let's go ahead and have a look, kind of going the opposite direction here. This is kind of just a general key here again for looking at the names of translating the ion names into formulas. If you have a prefix per and the suffix ate, that ion must have one more oxygen than the ion derived from the ternary acid, which we would consider to be the parent acid. If the name simply ends in ate, then it's got the same number of oxygens as the parent. If we have an ion name that ends in ite, then the acid from which that ion was derived must have had one fewer oxygen than the parent acid. And then again, prefix hypo, suffix ite, means that the acid from which that ion was derived must have had two fewer oxygens than the parent. So having a look at our example right here, the first one right here is the dihydrogen perphosphate ion. And looking at my prefixes and suffixes as the key, I have the prefix per and the suffix ate. Prefix per, suffix ate means we are looking at a species which has one more oxygen than the parent acid of this family, which was used to form the ions. So we're going to look at the root here of our acid here. That is the root phos. That root phos sounds very much like phosphoric acid. And looking on the bottom left-hand corner of your common ion sheets, we find the formula for phosphoric acid is the species H3PO4. So again, this is phosphoric acid. We now recognize that we have the prefix per, suffix ate, which means we have one more oxygen than the parent. So the acid from which we derived this ion, therefore, was the perphosphoric acid, which must have the formula, therefore, H3PO5. Again, one more oxygen due to the prefix per. So this guy right here is perphosphoric acid. And now we can look at the dissociation that yields the ions. Upon dissociation, the species H3PO5 would split apart into a hydrogen ion and H2PO5 1 negative. They can further split apart into H positive and HPO5 2 negative, which can then last split apart to H positive and PO5 3 negative. Now we don't need to name all of these different species in order to actually name the one that we're looking for or find the formula of the one we're looking for. We can pretty much identify out of this dissociation which of these ions we are dealing with. The prefix that we need in order to make this consideration here is the dihydrogen prefix there, which implies di meaning two. So the species of these ions which contains two hydrogens on it is this guy right here, H2PO5 1 negative, which according to our conventions would again be two hydrogens, which is prefix di, hydrogen. And then the acid that we used to make this ion was perphosphoric acid. Ic acids yield 8 ions, meaning this therefore is the perphosphate ion. Ic acids make 8 ions. All right, so a little bit of a mouthful there. Let's do one more quick example. I guess two more quick examples. Let's see, the dihydrogen borite ion. So start by looking up on your parent acid table. Find the parent acid of this family. We've got the root word here, bor, which refers to boric acid family. Boric acid listed on your sheet is H3BO3. We now check the name here. If this is boric acid, the parent, our ion has the suffix "ite," but no additional prefix. So suffix "ite" means we've got one fewer oxygen than the parent. So the parent acid, boric acid, our acid must therefore have been H3BO2 with one fewer oxygen, which would therefore be Bor-us acid. And we can now disassociate the acid. Splitting apart, we get H positive and H2BO2, 1 negative. And we can really complete the rest of that disassociation if we want to, but at this point we don't really need to go any further because this one has the same number of hydrogens as our ion we're looking for. So we can now name this thing. We have 2 hydrogens, which means this is again dihydrogen. And then we had the root bor, and then the ion formed here came from an us acid. Us acids yield ite ions, so this is the dihydrogen bor-ite ion. And again, if you needed one of the other ones from the disassociation, you could further go along, split this part more into another H positive and HBO2 negative, which could then, HBO2 2 negative, which could then further split apart to make H positive and BO2 3 negative. So again, we have the hydrogen borite ion and the borite ion if you needed those names too. All right, one more example down the bottom here. We now have the arsenite ion. The arsenite ion has the root name arsen there, which sounds very much like arsenic acid. The species listed on your parent acid sheet as H3ASO4. We notice here we have the suffix "ite," which again implies we have one fewer oxygen than the parent acid. So that means that the acid from which this ion was derived must therefore be H3ASO3, which would be arsen-us acid. So if this species now is arsenous acid, we can now disassociate it. It needs to be completely disassociated as we do not have any prefix hydrogen on this thing. So we're going to completely split this thing apart into H positive plus H2ASO3 1 negative, which then further splits apart to H positive and HASO3 2 negative, which then further splits apart to H positive and ASO3 3 negative. And now we can name the species we're looking for here. We had arsenous acid as the acid which formed the ion. Us acids make ite ions. There are no hydrogens on it, which means this is the one we're looking for right here. This is the arsenite ion. All right, so at this point we can now pretty much go both ways. We can take a name, give the formula, take a formula, give the name of a ternary acid ion. Moving along next here, I'm going to come back to this flowchart in just 1 minute. What I want to look at next, guys, is the ability to name a compound which contains a ternary acid ion. This is essentially putting all of your nomenclature skills together into one big cohesive whole at this point here. And the trick is that in order to name these compounds which contain ternary acid ions, this is going to be a metal plus a ternary acid ion, and we have to watch out for the same things we watched out for when we were dealing with simply binary ionic compounds. That is, some of these metals have multiple oxidation states, and in order to determine the oxidation state on a metal, we need to know what the charge on the ion which the metal is bonded to is. So I'm going to kind of follow through on the flowchart and see where we would find a species like the example that we have right here, the species CuHbO2. So looking on our nomenclature flowchart, let's follow the pathway. First question for the species, again, that was CuHbO2. Is it an element? Obvious answer there is no. Is it a binary compound made of 2 types of atoms? Certainly not as well. Next question, is it a ternary acid made up of hydrogen plus a nonmetal plus oxygen? Answer again here is no. So next question is this a metal plus a polyatomic ion? And in this case, we have copper, a metal, and then this ion, the ternary acid ion, HBO2. So the answer here is definitely yes. And the next question is, does the metal have more than one possible oxidation state? Looking up on your periodic tables, finding copper here, copper's element number 29, you'll see two oxidation states listed, +2 and +1. So the answer is yes. Which brings us down to this box right here, the naming conventions for naming metals plus polyatomic ions. We're going to name the compound by either using the stock naming system with the Roman numerals, or the ik and us naming system that we used earlier in our discussion of binary ionic compounds. According to the same conventions for the metal, and the real trick is we have to figure out what the polyatomic ion we're bonding that metal to actually is. So let's take a look at our example. We've got CuHbO2. We know this is a metal, copper, plus a ternary acid ion, and we're going to have to figure out what the charge on the copper ion is by looking at the ternary acid ion's charge. So let's start by naming the ternary acid ion. The species HbO2 is an ion derived from the dissociation of an acid in the boric acid family. Boric acid is the species H3BO3. So this is boric acid. If H3BO3 is boric acid, our ion has one fewer oxygen than boric acid has, which means we are interested, not in boric acid, we are interested in H3BO2, which means changing the acid name from ik with one fewer oxygen would be us. That is therefore bor-us acid. So we've got some ion derived from borous acid, and note now that our ion has one hydrogen left over from the dissociation. So to get to our ion, we would have to split this thing apart through its dissociation to H positive and H2BO2 1 negative, which then further splits apart to H positive and HBO2 2 negative, which then further splits apart to H positive and BO2 3 negative. Following our naming convention for these ions, us acids make ite ions, therefore BO2 3 negative is the bor-ite ion. And then our species that has two oxygens on it still, the one we're looking for, we now know has a -2 charge from that dissociation, so we can put that charge up on our ion now. Our species still has the hydrogen on it, implying this is the hydrogen borite ion. And at this point, we're now ready to go ahead and complete the naming of our compound. Recognizing that the ion HbO2 has a -2 charge, that implies the charge on the copper ion to make a neutral molecule overall must be +2, since the sum of the charges has to equal 0. Therefore, the ions we used to make this were Cu2 positive and HbO2 2 negative. So we can now name according to our conventions. This is either copper, parentheses, Roman numeral 2, to name the oxidation state, and then the name of our ternary acid ion is the hydrogen borite ion. So we're going to drop that suffix ion from the name. This is therefore copper 2 hydrogen borite. Or alternately, if you wanted to, you could also name, according to our Latin naming system here, the higher oxidation state of copper is the +2, which means this would be the cupric ion. So this is cupric hydrogen borite. So, big huge mess for solving this process. And again, the key idea is you need to find the oxidation state on the metal by looking at what is the charge on the ternary acid ion from its dissociation to get to that final answer. Let's take a look at another couple examples here. We've got the species FeClO2-3. So this one we've got an iron atom. Again, iron has multiple oxidation states. and then this ion ClO2, and we need to know the charges on these species here. So ClO2 is the place we're going to start. Find on your sheet the parent acid that looks most similar to this. You find on there that the species HClO3 is chloric acid. And then we have one fewer oxygen than that, which means we needed to disassociate HClO2, which would therefore be chlorous acid, with one fewer oxygen than the parent. If we disassociate HClO2, you'll notice we get H positive and ClO2 1 negative. Us acids make ite ions, therefore the ion ClO2 is the chlorite ion. And at this point, we now know the charge on that chloride ion is -1 from that disassociation. And we can now go ahead about naming our compound. Given that there are 3 of those -1 charged chlorite ions in our compound overall, that implies the charge on the iron ion to make a neutral molecule must therefore be +3. And therefore, the name of this compound is either iron 3 chlorite, or, according to our Latin naming system, ferric, the higher oxidation state of iron, ic chlorite. All right, and a couple more examples here, going the opposite direction. We're now going to go ahead and give the formula for potassium dihydrogen phosphite. So these are a little bit easier in my mind here. Potassium ion we can determine as an ion off of your periodic table. In the alkali metal family here, the charge on the potassium ion must be 1 positive, based upon the 1 valence electron that potassium atoms give up as they form ions. And then we've got this ion here, the dihydrogen phosphite ion. And start by, again, looking at the ternary acid parent of this family here. This root here is phos, which comes from phosphoric acid. Phosphoric acid, the parent acid of this family, is H3PO4. So this is phosphoric acid. We have the suffix ite. Ite ions come from us acids, which means this must have been derived from phosphorus acid. And us acids have 1 fewer oxygen than the parent, according to our ternary acid naming conventions, which means that must therefore have derived from H3PO3. So if we now disassociate H3PO3, we have H3PO3, the phosphorus acid, which would split apart into H positive ions and H2PO3 1 negative ions. And I can basically cut this off right now because I have the ion I need right here with 2 hydrogens attached to it. I need those 2 hydrogens because my prefix on the ion was the dihydrogen phosphite ion. So this ion right here, H2PO3 1 negative, is dihydrogen phosphite. And all that remains now is to determine the formula of my overall compound. We have potassium ions with a +1 charge, and H2PO3 with a -1 charge. And all that remains now is a simple crisscross, just the same way that we did with binary ionic compounds, to determine the ratio these ions combine together in to make a neutral compound, which would give me KH2PO3. So this is, again, potassium dihydrogen phosphite. And one final example here, and then we'll be done. Last example here is nickel-3 arsenate. So at this point, recognize that I've got a metal with multiple oxidation states. Please be very aware here that the 3 refers not to the number of nickels, but to the charge on the nickel ion. And then I've got a ternary acid ion. So we've got nickel-3 ions. The nickel-3 ion has a charge of 3 positive. And then we need to look to the arsenate ion, which comes from the root here, arsen, which is referring to arsenic acid. And looking on your common ion sheet, you find arsenic acid as the formula H3ASO4. This is arsenic acid. And you'll note ic acids here produce 8 ions. So this is in fact the acid, the parent that's going to derive, from which our ion is going to derive. So we're going to go ahead now completely disassociate this acid, recognizing that we don't have any hydrogens on the ion in the compound. So we'll split this part into H positive and H2 ASO4 1 negative, which then splits apart to H positive and H ASO4 2 negative, which finally splits apart to H positive and ASO4 3 negative. So ic acids make 8 ions, which implies, therefore, this is the ion we're looking for, the arsen 8 ion. And we can now go about giving the formula of our compound. The nickel 3 ion had a +3 charge. ASO4 3 negative was the arsenate ion with a -3 charge. We're going to crisscross those charges, make them into the opposite subscripts, and then reduce, recognizing that we need the smallest whole number ratio of the ions to one another, which implies the compound, therefore, is NiASO4. That is nickel 3 arsenate. So, that pretty much wraps it up, folks. You can now name compounds containing ternary acid ions. And again, the key things to watch out for here is that in order to determine the charge on the metal, you need to look to the non-metals, or the polyatomic ions in this case, to which it is bonded. To determine the charge on the ternary acid ion, you need to look to the dissociation of the acid which produced that ion in the first place. And that's pretty much that. Thank you very much for listening.